Welcome back to the deep dive. Have you ever found yourself wrestling with a complex problem? Maybe a tricky coding challenge or a really dense mathematical proof.
Oh, yeah, definitely.
And after trying a few approaches, you suddenly have that aha moment where everything clicks.
That feeling when it just falls into place.
Exactly.
Yeah,
You didn't just stumble on the answer, you reasoned your way to it. Well, that kind of sophisticated problem solving isn't just for humans anymore.
right.
We're now seeing advanced AI models that can think through these challenges, not just by being massive, but by becoming incredibly smart at inference time, when the model is actually put to work.
And what's truly fascinating here, I think, is that we're witnessing a significant paradigm shift.
How so?
Well, for a long time, the focus in AI was mostly on building bigger and bigger models, right? And then getting a single one-pass answer.
Yeah, just train it and ask it.
But now we're moving into this realm where models adapt, they deliberate, they even sort of reflect on their own thought processes.
Okay, interesting.
And today, we're diving deep into a groundbreaking approach called test time scaling, or TTS, and a new model that's really at the forefront of this, MetaStone-S1.
MetaStone-S1, got it.
This model manages to achieve performance that's, well, comparable to some of the most cutting-edge models out there, like OpenAI's O3 Mini, but with a surprisingly efficient and honestly elegant design.
Okay, comparable to O3 Mini, but more efficient. That's a big claim.
It is, and that's what makes it so interesting.
So our mission for this deep dive is to unpack the core insights from a recent research paper, Test Time Scaling with Reflective Generative Model, which introduces this MetaStone-S1.
Yep, that's the one.
And as always, we'll be focusing squarely on the technical ingenuity and the implications of the technology itself.
Right, the nuts and bolts.
We'll explore the really clever ways MetaStone-S1 learns to reason, how it evaluates its own thinking, that reflective part, and what that means for how we build and interact with powerful AI systems down the road.
It's all about how the AI finds its aha moments.
Exactly. So get ready for some aha moments of your own. Let's dive in. Okay, so let's set the stage a bit. We need to look at the broader AI landscape first. Over the past few years, it's fair to say we've seen an absolute explosion in large language models, LLMs.
Oh, completely. It's been wild.
We're talking about these incredibly powerful systems, right? Like OpenAI's GPT-4, Google's Gemini, Meta's Llama series.
Alibaba's Quinn, DeepSeek's R1, the list goes on.
Yeah, and these models have truly pushed the boundaries of understanding language, generating text, doing things that, frankly, seemed like sci-fi not that long ago.
For sure.
But what's crucial to grasp here, I think, is that their intelligence isn't just about what they learn during training, when they chew through massive data sets.
Right, that's only part of the story.
A significant part of their power comes from strategies used after training, during what we call inference time.
Exactly, the moment you actually ask it to do something.
That's when the model is actually asked to solve a problem or answer your query.
Precisely. And this brings us directly to test time scaling, TTS.
Okay, TTS.
At its core, TTS isn't about making the model itself bigger, adding more parameters necessarily. Instead, it's about leveraging additional computational resources at inference time to tackle the really challenging, complex problems.
So more effort when it matters most.
Think of it like a really skilled chess player. They don't just know the rules, right?
Of course not.
During a game, they take time. They weigh multiple possibilities, simulate scenarios, maybe reflect on potential outcomes before making their move.
Okay, yeah, that makes sense.
That strategic deliberation right there in the moment of action, that's kind of what TTS enables for AI. It allows the model to think harder when the stakes are higher.
That's a great analogy. A prime example of this, one that's really set a benchmark for this kind of advanced reasoning and coding, is OpenAI's O3 model.
Yep. O3 is a big one in this space.
The paper we're discussing highlights that O3 achieves its really impressive capabilities largely through these very TTS techniques. Can you walk us through some of the specific methods O3 uses? How does it think harder?
Certainly. So OpenAI's O3 model uses a mix of pretty sophisticated techniques. We're talking massive sampling, intelligent candidate scoring, and exhaustively searching over multiple reasoning paths.
Multiple paths, so not just one shot.
Definitely not. For instance, when it's tackling really complex evaluations, like problems from the ARC-AGI dataset, which tests general intelligence or, say, competitive coding challenges.
Yeah, those are tough.
Right. O3 has been observed to generate an astounding number of candidate samples for just one query, sometimes up to 124 unique attempts.
Wait, 124. 1,000 different tries for one problem.
Yep. And it's not just slightly different wording. We're talking exploring fundamentally different logical pathways to find a solution.
That idea,
Yeah.
a model generating 1,000 potential solutions, that's really mind-blowing. What does that fundamentally change about how we think of AI thinking? Does it mean the traditional one-pass model where AI just spits out one answer is kind of obsolete for complex stuff?
Well, obsolete might be strong, but it definitely marks a profound shift. The traditional one-pass model certainly still has its place, right? For simpler, more straightforward queries where you just need speed and efficiency.
Like basic translation or summarizing something short.
Exactly. But for the really difficult, high-stakes problems that need genuine reasoning, multi-step math, debugging complex code, maybe even intricate legal
Right,
analysis,
things where you can't just guess.
the limitations of a single immediate pass become really evident. These problems often have lots of potential pitfalls. They require a nuanced exploration of the solution space.
So for those tricky tasks.
Yeah, for those complex reasoning tasks, the one-pass approach is increasingly just not enough. TTS models, because they dynamically adapt and explore possibilities, they're moving towards near-human performance precisely because they're doing this kind of deliberate thinking at inference time.
So the thinking is the key difference.
It highlights the immense value of strategic deliberation, even if it means using substantially more compute power right at that inference stage. It's a trade-off, but one many applications are now willing to make for better accuracy and robustness.
Okay, so we've got test time scaling, smarter inference, but the paper breaks TTS down further into internal and external approaches. Let's start with internal TTS, also called sequential scaling. What's the main idea there? How's it different from that massive sampling we saw with O3?
Right, so internal TTS focuses on getting the model to generate a longer explicit chain of thought, or COTI,
Chain of thought. Yeah, heard of that.
before it gives you the final answer. So unlike O3, which might generate many separate full solutions in parallel, internal TTS is about a single, long, detailed reasoning process unfolding step by step.
Okay, so one long thought instead of many short ones.
Pretty much. Models like OpenAI's O1 and DeepSeek R1 are good examples. They essentially think out loud internally, planning their solutions step by step, and then they use that very thought process to guide the final outputs.
Like showing your work.
Exactly like showing your work. And the key benefit is that a detailed CONI can really help the model self-correct errors midstream. It helps decompose complex problems into smaller, more manageable bits.
Which leads to better performance, presumably.
Generally, yes, substantial performance improvements in many cases. It's like watching someone work through a problem, articulating each step.
That sounds super intuitive. Breaking it down, finding errors. But the paper also mentions this fascinating, almost paradoxical challenge, the risk of overthinking. What does that even mean for an AI? Can it think too much?
It's a crucial point. Research, including work by Chen and others, has shown that sometimes, excessively long or convoluted reasoning trajectories can actually hurt performance.
Really? How?
It's not simply more thinking is always better. An AI, just like us sometimes, can get lost in its own generated thoughts. It might generate irrelevant steps, or steps that lead it down completely the wrong path, basically adding noise instead of signal.
So how long is too long? Is there a magic number?
That's the tricky part. Finding that sweet spot for internal deliberation is key. It's a fine line between breaking down a problem effectively and just generating, verbose, redundant, or even wrong internal monologues that steer the model away from the right answer.
Interesting. So without good guidance, that internal chain of thought could become a liability.
It definitely could.
Okay, so if internal TTS is sequential, detailed thought, then external TTS must be about parallelism, right? Can you explain that distinction? How does it tackle problems differently?
Exactly right. External TPS, or parallel scaling, uses a different strategy entirely. Instead of one long thought process, it generates multiple distinct reasoning trajectories and their candidate answers all at the same time, in parallel.
Okay, multiple attempts at once.
Then a separate component, usually called a reward model, comes in to score all these parallel attempts and pick the best one.
So it generates options and then judges them.
Yep. And this approach has proven to be quite effective, often boosting performance more than just relying on whether the final answer was right or wrong. It's kind of a shotgun approach. Generate many potential solutions, then use a smart judge to pick the winner.
And what are some of the main algorithms or methods for this external approach?
The paper mentions several key ones. Best of n sampling is maybe the most straightforward.
Best of N sounds like what it is.
Yeah, the model generates n different outputs, and then a process reward model, or PRM, evaluates them and picks the best.
Okay.
Then there are more fine-grained methods like beam search, diverse verifier tree search, and Monte Carlo tree search, MCTS.
MCTS, okay.
These go beyond just picking the best final answer. They actually search and evaluate at the step level within multiple reasoning paths, also guided by these PRMs.
Process reward models, PRMs. You mentioned them for best of N too. They sound important.
They are crucial. PRMs are designed to evaluate the LLM's output not just at the end, but step by step. This fine-grained feedback leads to much better TTS performance compared to, say, outcome reward models, ORMs, which only care if the final answer is right or wrong.
So the PRM is like a detailed rubric for each step, not just a pass-fail in the whole thing. That makes a lot of sense for complex reasoning. But the paper also highlights a big challenge with PRMs, right? What's the bottleneck there?
You're absolutely right. The major bottleneck for training PRMs traditionally is their reliance on high-quality, task-specific, annotated data.
Annotated data, meaning humans labeling stuff.
Exactly. For a PRM to learn well, it needs examples where human experts have meticulously gone through each step of an AI's reasoning and labeled it. Correct, incorrect, maybe suboptimal.
Wow, that sounds like a ton of work.
It is. This kind of detailed step-level annotation is incredibly expensive, time-consuming, and just plain difficult to get, especially for complex reasoning problems where the paths can be super intricate and varied. This data scarcity has really been a major barrier to scaling up PRMs.
And there's also that interesting point about model size and strategy choice. Liu et al. Noted that for models under 32 billion parameters, search methods like beam search seem better. But for 32 billion or more, sampling like best of N works better. Why that split? Does it tell us something fundamental?
It's a really fascinating empirical finding. It strongly suggests that larger models, with their huge parameter counts and extensive training, might just inherently generate a more diverse and higher quality set of initial candidates right off the bat.
So they're better brainstormers just because they're bigger.
Kind of. Their internal representations are so rich that even just sampling a bunch of outputs gives you a really strong pool to choose from. For these giant models, the task of selecting the best one becomes easier and more effective than meticulously searching step by step.
Because step-by-step search would be computationally insane for a huge model.
Exactly. Imagine running a detailed step-level search across 32 billion parameters over and over. The cost would be astronomical. Smaller models, though, with their more limited capacity, might struggle to generate truly diverse or top-quality initial ideas on their own.
So they need more guidance.
Right. They benefit much more from the structured step-level guidance that search algorithms provide to navigate the solution space effectively.
So it's not one size fits all for inference strategies.
Definitely not. This interplay between model size and the best TTS strategy is crucial. It raises questions about emergent properties. What happens when a model gets big enough that sampling becomes better than searching? It's a reminder that efficiency often comes from really understanding your tool's capabilities and limits.
Great point. It's about picking the right tool for the job. And the paper notes these internal and external approaches aren't mutually exclusive. They can actually work together.
Absolutely. The synergy can be really powerful. Imagine a model that generates a detailed internal thought process and then uses a robust PRM to pick the best among several of those detailed processes.
Best of both worlds.
Exactly. You combine the self-correction of internal deliberation with the robustness of parallel exploration and external checking. It allows for potentially more comprehensive and accurate reasoning, really pushing the boundaries by stacking these complementary techniques.
Okay, we've mapped out the landscape internal versus external TTS, the challenges like that costly annotation for PRMs. Now let's zero in on MetaStone-S1, the star of this paper. It introduces this ingenious approach to tackle those exact hurdles. How does it manage to blend generation and self-evaluation so effectively? What is this reflective generative form?
Right, so MetaStone-S1 primarily focuses on the external TTS approach, but it introduces this novel reflective generative form, specifically to get around the extra computation and expensive annotation problems we just talked about.
Okay, yeah, what's the secret sauce?
It really boils down to two key innovations. First, they developed a unified interface for the policy model, the part that generates text, and the process reward model, the part that judges it.
Unified. So they're combined somehow.
Yes, exactly. Instead of having two separate, potentially large networks, MetaStone-S1 shares the core neural network backbone between the policy model and the PRM.
Ah.
This fundamentally allows it to do both things: predict the reasoning trajectory, generate the thought process, and select or score that process within a single integrated network. This makes parallel processing incredibly efficient.
How efficient are we talking?
Remarkably efficient. For the 32 billion parameter version, adding the scoring capability introduces only about 53 million extra parameters. That's tiny overhead for such a critical function.
Wow, 53 million on top of 32 billion. That is small. So it's like one brain doing both creating and evaluating. Does that mean it gets a more holistic view, or could the critic be too close to the creator to spot subtle flaws?
That's a really insightful question. It's a valid concern, right?
Right.
Could they be too intertwined? But the design seems to handle that pretty well.
How?
While they share the main backbone, the reward model part, they call SPRM, still has its own small specialized head. It's basically a binary classifier that does the actual scoring.
So it's integrated but still specialized.
Exactly. It leverages the rich understanding from the generative part, but it develops its own specific skill in judging quality. Think of it less like a writer editing their own work blindly, and more like a skilled editor who grew up with the writer, understands their style, their common mistakes, but still keeps that objective distance needed to improve the work.
Okay, that makes sense. An integrated yet specialized design.
And that's key to its efficiency and effectiveness. It builds a more coherent, self-aware reasoning system without losing that critical judgment.
And the second innovation, this Self-supervised Process Reward Model, or SPRM, that sounds even more groundbreaking, especially given that annotation bottleneck we discussed. It claims to eliminate reliance on costly process-level annotation.
Yep.
That's huge, right? If you don't need humans labeling every single step for training, that just opens up so many possibilities for scaling AI development. How on earth does it learn without that explicit step-by-step guidance?
It's truly a game changer for scalability, and yeah, it's quite ingenious how it works. The SPRM learns high-quality reasoning trajectory selection directly from outcome rewards.
Outcome rewards. So just whether the final answer was right or wrong?
Basically, yes. It learns just from knowing if the final answer it produced was correct or incorrect, and it does this in a self-supervised way.
How? How does it figure out which steps were good or bad from just the final result?
It's like teaching a student to improve their problem solving just based on their final test score without marking their homework steps. The SPRM essentially infers the quality of its intermediate steps from that ultimate success or failure. It uses a clever mechanism, which we'll get into, involving dynamic weighting based on its own predictions versus the final outcome.
Okay, dynamic weighting.
This lets it filter out noise and focus on the most informative examples during training. It completely bypasses the need for human experts to painstakingly label millions of tiny reasoning steps, which, as we said, has been a monumental, cost-prohibitive task.
Wow. That basically sidesteps the biggest barrier to using PRMs widely.
Pretty much.
And MetaStone-S1 also offers controllable reasoning effort modes. What does that mean for someone using it?
It gives you flexibility. You can explicitly control the thinking length, basically the number of candidate trajectories the model generates and evaluates before giving an answer.
Like turning a dial for thinking power.
Kind of. It offers low, medium, and high reasoning modes. These correspond to generating K2, K8, and K32 candidate solutions, respectively.
Okay, 2, 8, or 32 attempts.
Right. So it gives practitioners direct control. You can balance the compute cost of inference with the performance level you need, depending on how critical or complex the task is. Low effort for quick internal queries, maybe high effort for something really important where accuracy is paramount. You make the trade-off.
This all sounds incredibly sophisticated. Let's really get into the nitty-gritty now. How does this unified interface actually work in practice? How does the model generate its thinking and then turn around and judge it?
Okay, so in practice, the policy LLM part of MetaStone-S1 generates responses that explicitly include a thinking process, right? A visible chain of thought.
Marked somehow.
Yeah, it's clearly marked off by special tokens like think and think. These basically signal, okay, here's the internal deliberation.
Got it.
And the SPRM, the judging part, as we said, shares that same backbone. So it has access to all the knowledge learned for generating text, which it can then use for evaluation, but it funnels this information into its own small, specialized SPRM head, which is essentially just a binary classifier designed specifically for scoring these internal reasoning steps.
Okay, generates the thought between tokens, then the SPRM head scores it. How does it evaluate that whole thinking process? The paper mentions 2 steps. Step segmentation and trajectory score prediction. So let's start with segmentation. How does it chop up a long thought into individual scorable steps?
Right, the segmentation part is actually quite elegant because it's simple and efficient. Instead of inventing new custom tokens just to mark step endings or needing complex fine-tuning.
Which would add complexity.
Exactly. MetaStone-S1 cleverly uses existing tokens that the policy model's tokenizer already understands. Specifically, it looks for tokens containing a period followed by two new lines.
Ah, like a paragraph break almost.
Kind of, yeah. It uses those as...
All right, word by word.
It's highly specialized for that very local context needed to decide the next word, like a proofreader just focused on the next character. But the hidden representations from deeper layers, especially layers like the second to last one,
Yeah.
they generally capture a richer, more abstract, more holistic contextual understanding of the entire preceding sequence or reasoning step.
A bigger picture view.
Exactly. It provides a more comprehensive basis for judging the quality of a reasoning step, not just its immediate linguistic output. These richer representations are then fed into that small SPRM head to predict a process score for each individual step. It's like stepping back from proofreading to actually grasp the meaning and logic of the whole paragraph.
Okay, that makes sense. Use the layer with the richer context for judgment. And once it has scores for each individual step, how does it combine them for the whole trajectory? It uses a geometric mean, which you mentioned is sensitive to low values. Why that specifically instead of just averaging them?
The choice of the geometric mean is really significant here. As you said, it's highly sensitive to low values. If even one step in the reasoning path gets a very low score, signaling a critical error or a big logical flaw,
Yeah.
the overall geometric mean for the entire trajectory gets pulled down significantly, much more dramatically than a simple arithmetic average would.
Why is that good for reasoning?
It makes perfect sense for evaluating a chain of reasoning. One critical error, one bad calculation, one faulty assumption can invalidate the whole process even if all the other steps were perfect.
Right. A chain is only as strong as its weakest link.
Precisely. The geometric mean enforces that. It helps flag those fundamental weaknesses effectively. An arithmetic average might just smooth over a critical error, giving you a misleadingly high score that doesn't reflect the real quality.
Crucial distinction. Okay, so that ensures robustness. Now, how is this whole system optimized? How does it learn? The paper introduces SPR loss, self-supervised process reward loss. It mentions this challenge of noisy labels, correct answers from bad steps, wrong answers from mostly good steps. How does SPR loss handle that messiness?
This is where that self-supervised dynamic weight comes into play. It's really clever. The core problem is exactly that noise.
Yeah.
You can't just blindly assume every step leading to a right answer was good or every step to a wrong answer was bad.
Right, logic can be messy.
SPR loss ingeniously mitigates this. It calculates the learning signal of the loss only if the SPRM head's own prediction for a step is consistent with the final answer's correctness.
Consistent, meaning?
If the SPRM thinks a step is good and the final answer was correct, it learns from that step, wait whip was 1. If it thinks a step is bad and the final answer was wrong, it learns from that too. But if there's an inconsistency, like the SPRM thinks a step is good but the final answer was wrong, or vice versa, then we is set to 0.
So it ignores the confusing examples where its internal judgment doesn't match the final outcome.
Exactly. This dynamic filtering lets the model learn from the less noisy, more reliable samples. It progressively focuses on the most representative steps of clearly correct and clearly incorrect solutions. It's a sophisticated way for the model to learn discrimination using only outcome rewards without needing explicit human labels for every single intermediate step.
It's like an internal filter for its own learning process. Very smart.
It allows it to self-refine its judgment capability effectively.
So finally, how does this all come together at inference time? I asked MetaStone-S1 a question, set it to high reasoning mode, K32. What happens under the hood before I get my answer?
Okay, so the inference process, shown in Figure 2b of the paper, happens in 3 main steps. First, for your question, the policy model samples K-candidate thinking, processes those 32 reasoning trajectories in your example.
Step 1, generate options.
Step 2, the SPRM rapidly evaluates the steps within each of those 32 processes. It calculates a process score for each step, combines them using that geometric mean, and gets a final score for each of the 32 trajectories.
Step 2, judge the options.
And step 3, the reasoning trajectory with the highest final score is chosen as the best thought process. This selected high-quality trajectory then guides the policy model to generate the final answer it gives back to you.
Step 3, pick the best and answer.
Right. It's a complete efficient cycle, generate possibilities, internally evaluate their quality, and then perform based on that refined self-reflection.
Okay, this all sounds incredibly clever technically, but the proof is in the pudding, right?
Yeah.
How does MetaStone-S1 actually perform when you test it on tough benchmarks?
Yeah.
What was the experimental setup and what were the key results that jumped out?
Right, the performance. The researchers did a pretty rigorous evaluation. They tested MetaStone-S1 across 3 sizes, 1.5 billion, 7 billion, and 32 billion parameters.
Okay, small, medium, large.
And these weren't built from scratch. They were initialized from existing strong open source models like DeepSeek-R1 DistillQ and QWQ32B, so they started from a good baseline.
Makes sense.
And a critical point on efficiency, which we talked about. Adding that SPRM head was minimal overhead. Only 5 million extra parameters for the 1.5B model, 26 million for the 7B, and just 53 million for the 32B model.
Tiny additions for a big capability.
Exactly. The training data itself was about 40,000 high-quality math examples, carefully curated from public sources, using a multi-agent cleaning framework to ensure quality.
Okay, good day.
And during inference, they tested it in those 3 modes: low K2 candidates, medium K8, and high K32.
What benchmarks did they use to really push these models, especially on reasoning?
They used a diverse and really challenging set. For math reasoning, they used AM 2024 and AM 2025 problems from the American Invitational Mathematics Examination, known for being very difficult multi-step stuff.
Okay, top-tier math problem.
For out-of-distribution tasks to check generalizability, they included live Codebench programming problems from coding competitions. That requires precise logic and problem decomposition.
Hunking challenges, right?
And they also used CEVAL, a broad Chinese evaluation benchmark covering lots of knowledge and reasoning skills.
So math, coding, general knowledge?
Yeah.
Pretty comprehensive. How did they measure success?
The main metric was pass at 1. Basically, the percentage of problems solved correctly on the first try, and they averaged this over 64 repetitions to make sure the results were stable and statistically significant, not just luck.
Okay, pass at 1 averaged over many runs. Got it.
Hmm.
All right, moment of truth. Looking at Table 1 and Figure 1 in the paper, what did they find? How did MetaStone-S1 do?
The results are quite compelling and very consistent. The reflective generative form consistently and significantly boosts performance over the baseline model, that's the policy model, without the reflection across all the sizes they tested, and particularly on those tough math reasoning tasks.
How big were the boosts?
For example, the 1.5 billion parameter MetaStone-S1 in its high reasoning mode got an 18.6-point gain on AME24 and 10.5 points on AME25 compared to its baseline. That's huge. Even on coding and C-eval, the gains were smaller but still stable and positive. It clearly shows the value of that reflective mechanism.
Wow, an 18-point jump on AM. That's substantial for just adding that small SPRM in the reflective process.
Yeah.
How does it stack up against other big open source models, especially larger ones?
It really punches above its weight, showing remarkable efficiency. MetaStone-S1 1.5B low, the smallest one on low effort, already beat other 1.5B models like DeepScaler 1.5B and R1 DistillQ 1.5B across the board.
Okay, good start.
But even more strikingly, MetaStone-S1 1.5B high, still just 1.5 billion parameters, managed to outperform much larger models like the 7B R1 DistillQ and the 8B R1 DistillLlama on AME24. It scored 57.9% versus their 55.5%.
A 1.5B model beating 7B and 8B models. That really highlights the efficiency.
Absolutely. It shows the power of the lightweight SPRM and the reflective design. Similar strong gains for the 7B Metastone model, too. It's really a testament to smart design winning over just raw size sometimes.
Okay, and this is where it gets really exciting for the broader AI community. How does the 32 billion parameter MetaStone-S1, an open source model, compare to the closed source giants like OpenAI's O3 Mini, GPT-4o, Claude 3.5? This is often where open source struggles.
This is indeed the benchmark breakthrough the paper emphasizes. MetaStone-S1 32B high achieved superior results on the math tasks compared to all the listed open source models, even bigger ones. It got a plus 4.4% boost on AME24 over the best comparable open source model.
Better than other open source. What about the closed ones?
It also outperformed Claude 3.5 Sonnet and GPT-4o on those specific math benchmarks, which is incredible for an open source model.
Wow. Okay.
But the most crucial finding, I think, is that MetaStone-S1 32B achieves comparable performance with the medium level of OpenAI's O3 Mini.
Comparable to O3 Mini. Seriously.
Yeah. For example, on AME24, MetaStone-S1 32B high scored 85.2% versus O3 Mini's 79.6%. On C-eval, MetaStone scored 89.7% versus O3 Mini's 75.9%.
So it's beating O3 Mini Medium on some key benchmarks.
On those, yes. Now, O3 Mini still has an edge on some other tasks, like Live Code Bench, the coding one, but MetaStone-S1's overall competitiveness for a 32B open source model is truly remarkable, especially given its architectural efficiency and that it's likely using fewer parameters than many top closed source models. It's a huge step for the open source community.
So what does this mean for you, the listener, especially if you're working in AI development or research? It really suggests we're getting closer to a future where these highly capable AI models, the kind previously locked behind closed doors because they were so huge or proprietary,
And inaccessible to many.
they might become accessible and deployable with significantly less computational overhead and potentially more transparency, being open source. This is a powerful step towards wider adoption of advanced reasoning AI, getting these cutting-edge capabilities into the hands of more developers and researchers.
It could really accelerate innovation across the board, moving advanced AI beyond just a few big labs. Hashtag tag Z6, uncovering the aha moment and scaling laws in AI. Beyond just the raw performance numbers, which are impressive, the paper dives into some really insightful analyses about why MetaStone-S1 works so well. What fundamental principles is it tapping into? One key aspect is its adherence to a scaling law for these reflective generative models. It's visualized really nicely in Figure 3.
A scaling law. That sounds fundamental, like physics. What does the scaling law tell us about computation versus performance in these reflective models?
It reveals a crucial relationship. They looked at the total reasoning computation used at inference time, which they define as C, the model's parameters times the total reasoning tokens generated.
Okay. Total compute effort.
And what they found is a clear positive correlation between the final performance and the logarithm of this computation budget, C.
Logarithm. So diminishing returns.
Exactly. It implies that to get a linear gain in accuracy, you often need an exponential increase in computation, either by making the model exponentially bigger or by exponentially increasing the reasoning lengths the number of candidates it evaluates.
So intelligence is computationally expensive, fundamentally.
It reinforces that idea, yes. But crucially, there seems to be a practical limit. The performance gains tend to slow down significantly once the total reasoning length scales beyond about 32 times the baseline. So going from best of 1 to best of 32 gives big gains, but going much beyond best of 32 might not be worth the extra compute.
Diminishing returns kick in hard around K32.
Right, which is critical information for anyone trying to optimize resource allocation for deploying large AI models. You can't just throw infinite compute at it and expect infinite improvement. There's an optimal investment point.
That's a super practical insight for real-world systems. But maybe the most captivating part for me, the part that really resonates with human learning, is this idea of the aha moment of the reflective generative model. Figures 4 and 5 illustrate it beautifully. What is this phenomenon? What does it tell us about how an AI learns to critique itself?
The aha moment, it refers to this distinct, almost dramatic point during MetaStone-S1's training, where things just click for the model. Specifically, the optimization trends for correct versus incorrect reasoning trajectories start to sharply diverge.
Diverge? How?
In the early stages of training, before this aha moment, the model basically can't tell the difference between good and bad reasoning steps. If you look at the internal scores the SPRM gives them, they follow very similar noisy trends. It's almost guessing.
Okay, it's confused initially.
But then, after a certain number of training steps, typically a few thousand samples in their experiments, something fundamentally shifts. It's like the model suddenly gets it.
Gets what?
It starts to judge correctness based on the actual content and logic of the reasoning itself, not just relying on the final outcome signal. The scores for correct reasoning paths start climbing consistently, while the scores for incorrect paths start falling sharply. A clear gap opens up between them.
Wow. That's incredible. It's like the AI suddenly wakes up or develops genuine understanding of good versus bad reasoning, not just correlation, but something deeper.
It certainly looks like a qualitative leap in its understanding, not just gradual quantitative improvement.
Give a specific example from the paper. Show us this shift in action.
Yeah, they have a perfect illustration. It's from a math problem where the model makes a specific calculation error. It confuses epsilon and epsilon plus 1 during simplification.
Okay, it's definite mistake.
Before the aha moment in training, the SPRM gives this exact incorrect step a score of 0.52, basically a coin flip. It can't confidently say if it's right or wrong.
Just guessing.
But after the aha moment, looking at the exact same incorrect step, its score dramatically drops to 0.12. It now correctly and confidently identifies it as low quality, as an error.
That's a clear demonstration, from 0.52 down to 0.12 for the same error,
Yeah.
just because the model trained past that aha point.
Exactly. It shows the model learning to critically evaluate its own intermediate steps. And this aha moment also strongly validates the SPR loss function we talked about. It shows SPR loss successfully refining the SPRM head, leading to that clear functional score gap needed for effective test time scaling. The internal self-correction mechanism truly kicks in.
This self-correction and the aha moment are really impressive narratives. But let's dig into the hard empirical evidence. What did the ablation studies where they systematically took parts away or changed things reveal about how much SPRM and its self-supervised optimization actually contribute?
The ablation studies provide really strong backing for the design choices in MetaStone-S1. If you look at Table 2 and Figure 6 in the paper, our SPRM, remember, with its tiny extra parameter count, just 5 million for the 1.5B model.
Yeah, super small.
It actually achieves higher performance than separate, much larger reward models. That includes a massive 72 billion parameter outcome reward model, ORM, and even other separately trained process reward models, PRM.
Wait, the tiny integrated SPRM beat a separate 72B reward model?
Yep. It powerfully demonstrates that sharing parameters between the policy and reward models, combined with that clever self-supervision, genuinely generates high-quality guidance without needing huge separate models. It's a massive win for computational efficiency, doing more with less.
So it's not just smaller, it's actually better in these tests. That's remarkable, especially for open source efforts where compute is often tight. And Figure 6 shows SPRM consistently outperforming others across different numbers of candidates. What about its generalization? Is it just good at math, or does it learn a more fundamental critique skill?
That's precisely what makes SPRM so impactful. It shows strong zero-shot generalization, meaning it performs remarkably well on completely different out-of-domain tasks like the live code bench coding problems.
Yeah, without being trained on coding problems.
Exactly. Without any task-specific fine-tuning or seeing any coding data during its SPRM training phase, it just applies the evaluation skills it learned primarily from math problems to a totally new domain.
That's fascinating, because it's not just memorizing math patterns. It seems to be capturing some universal patterns of good versus bad reasoning that work across different fields. Why is that so important?
It means the SPRM isn't just pattern matching. It seems to be learning a more fundamental, domain-agnostic meta-skill, evaluating logical progression, identifying flaws, discerning high-quality thought processes in general. This massively boosts its applicability. You don't need to do extensive, expensive domain-specific training and annotation for every single new task you want the AI to tackle.
Making it much more versatile and efficient to deploy on new problems.
Exactly. In a world where AI needs to handle increasingly diverse challenges, this generalizability is key. It hints at a deeper understanding of reasoning quality, making the model more adaptable and robust. It's a step towards truly versatile AI.
And the paper also have those visualizations in Figure 7, showing SPRM scoring steps. What do they reveal about its precision?
Those visualizations are really insightful. They clearly show SPRM assigning low scores to specific, flawed steps within a reasoning path. For instance, in one math example, it accurately flags a logical error where the model misunderstood a variable definition.
Catches logical errors.
And in another case, it correctly flags a simple but critical calculation error, 9 by 21 plus 7, computed as 193 instead of 196.
Catches calculation errors too.
This ability to pinpoint errors at such a granular level is invaluable, both for debugging these complex AI systems and potentially for giving users much better insight into where and why an AI's reasoning might have gone wrong. It adds a layer of interpretability often missing in these big black box models.
That detail is incredibly valuable for trust and reliability, especially in critical uses. Okay, one last ablation check. The effectiveness of the self-supervised optimization, SPR loss itself. How did comparing it to a standard loss function, like binary cross-entropy loss, BCE loss, show its value?
Right. Table 3 and Figure 8 cover this. SPR loss consistently achieves significantly larger performance gains compared to using standard BCE loss, where you just use the final answer correctness as the label for every step.
So SPR loss is definitely better than the naive approach.
Much better. And Figure 8 illustrates why. SPR loss generates a much larger score gap between correct and incorrect solutions. This indicates a much stronger ability to discriminate between good and bad reasoning.
A clearer separation.
The key takeaway is really important. Treating final answer correctness as a direct, noisy label for every intermediate step just doesn't work that well. SPR loss, with its intelligent self-supervised signals and dynamic weighting, effectively mitigates that noise. It leads to much more stable, accurate, and robust training for the process reward model.
So the sophisticated loss function is crucial.
It really highlights the power of intelligent loss function design over simpler methods, especially when dealing with the complexity and noise inherent in generated reasoning paths. It optimizes the learning process itself.
Okay, so MetaStone-S1 is clearly a significant advance on its own. But the paper also hints at future directions, specifically its natural suitability for integration with Monte Carlo tree search, MCTS. Can you explain that connection? Why is SPRM a good fit there?
Yeah, the synergy looks quite promising. Because SPRM produces these high-quality scores for each individual step in a reasoning path.
Right, that step-level granularity.
MetaStone-S1's reflective form is naturally well-suited for step-level search methods like MCTS. In MCTS, you're building the search tree of possible reasoning steps, exploring different branches to find the best path.
Okay.
Traditionally, evaluating each node, each potential step in that tree, often requires running costly full simulations all the way to the end of the reasoning path just to estimate its value.
Which sounds computationally expensive.
Very. But with SPRM, you might not need those full simulations. SPRM can potentially directly and efficiently estimate the value or quality of each node during the search itself. It could make evaluating each expansion in the tree much faster.
Speeding up the search significantly.
That's the potential, yes.
And did they show any initial results? Did integrating with MCTS actually help?
They did. Table 4 shows some initial results for the 1.5B MetaStone model on AME24 using MCTS. By increasing the number of searching tokens allowed in MCTS, they improved performance from a baseline of 39.3% without MCTS up to 52.8% with MCTS.
Wow, that's a pretty solid gain. From 39% to nearly 53%.
It definitely demonstrates that SPRM can provide effective step-level guidance during a reasoning search, enabling better exploration of the solution space.
Okay, so that's promising. But the paper also notes that even with these gains, the MCTS performance was still lower than the best-of-n sampling strategy they used earlier. So what's holding MCTS back here? If SPRM is so good at step evaluation, why isn't MCTS winning overall? What's the challenge?
That's a critical question, and likely an area for future work. It seems to boil down mainly to the inherent computational overhead of these complex tree-based search methods.
Even with SPRM helping.
Even with SPRM making node evaluation more efficient, the sheer process of exploring every branch in a deep, potentially vast search tree remains incredibly demanding. The computational cost often leads to incomplete searches in practice. You just can't explore the whole tree within reasonable time or compute limits.
So the search space is just too big for MCTS to cover effectively, even with faster evaluations.
It seems so, especially compared to best of N. While MCTS offers a more structured, granular search, its exhaustive nature often becomes computationally prohibitive at scale. This can make best of N, which is more parallel and less sequential in its exploration, the more pragmatic choice, especially for very large models or tight time constraints.
But the gains still show potential.
Absolutely. The observed gains over the baseline clearly validate the potential for integrating SPRM with more advanced, perhaps more optimized or pruned search-based inference methods in the future. Making these powerful but intensive search methods more practical for large-scale AI is definitely an active research area. So if we step back and connect this to the bigger picture, what we've really seen with MetaStone-S1 is genuinely exciting. It's not just, another powerful LLM dropped onto the pile.
Right, it's different.
It's a model that has demonstrably learned to reflect on its own reasoning process. By unifying generation and self-evaluation, and crucially, by learning how to do this without needing those incredibly expensive step-by-step human annotations, MetaStone-S1 represents a significant leap forward.
Towards what?
Towards creating AI that's more efficient, more adaptable, and still highly capable at complex reasoning. It's a foundational piece of work, I think, that could really influence how future AI systems are designed for problem solving, putting more emphasis on this kind of intelligent self-critique.
That's right. That aha moment for the model. The scaling laws showing predictable, if costly, improvement, and its ability to compute with top-tier, closed-source models while being much more parameter efficient. It all points towards a future where advanced AI reasoning isn't just locked away.
Becoming more accessible.
Exactly. More accessible and powerful for a wider range of applications. This deep dive has really shown us that the future of AI isn't just about raw power, but about intelligent, self-aware processing. And critically, about doing more with less compute.
Well said.
So what does this all mean for you listening? The next time you see an AI tackle a really complex problem, you might just wonder, did it have its own aha moment along the way? Did it internally debate 32 different ways to solve it before giving you the answer?
Makes you think differently about the process.
It does. And think about the implications. If models can genuinely get better at understanding and self-diagnosing their own reasoning errors in real time, how much more reliable, how much more robust could they become? Especially in truly critical applications, medicine, engineering, finance, where correctness and trustworthiness are absolutely paramount. This ability to self-critique isn't just academic. It could open doors for AI in fields where older models might be too opaque or too prone to unrecoverable mistakes. That's something profound to mull over. And remember, to stay updated on the latest AI and ML research papers like the one we discussed today, visit our webpage. The link is in the bio.